Proxima B often appears on lists of places that may be capable of supporting life beyond Earth. It is the closest known exoplanet to us, located within the region where liquid water could exist on the surface. At just over 4 light-years from Earth, Proxima B quickly became one of the most extensively studied exoplanets. But calculations of Proxima B's orbit have led to a conclusion that cannot be ignored. This planet may always keep one side facing its star. One half of the world could be locked in permanent daylight, while the other half may never witness a sunrise. And it is precisely at the boundary between those two halves that the real challenge begins to emerge. If Proxima B truly has the potential to support life, then where would life exist on a planet like this? Most potentially habitable exoplanets known to us are located very far from Earth. Proxima B is different in one important way. It is located within the closest known star system to Earth. That system is Alpha Centauri. But behind that point of light is not a single star. It is a system of 3 stars bound together by gravity. The 2 largest stars are Alpha Centauri A and Alpha Centauri B. Much farther away is Proxima Centauri. This is a red dwarf star that is significantly smaller than the other 2 stars in the system. Its mass is only about 1/8 the mass of the Sun. Its brightness is also tens of thousands of times lower. If viewed with the naked eye from Earth, we would not be able to see it at all. However, this small star is actually the closest member of the entire Alpha Centauri system to us. The distance from Proxima Centauri to Earth is about 4.24 light-years. Light, which travels at nearly 300,000 kilometers per second, still requires more than 4 years to cross that vast expanse. It is this distance that makes Proxima Centauri a special target in many exoplanet studies. Not because it is larger. If humanity ever succeeds in traveling to another star system, Proxima Centauri would almost certainly be among the first destinations. For many years, Proxima Centauri itself was not considered an ideal candidate in the search for life. Red dwarf stars are typically small, cool, and highly active. They can produce energy outbursts far more powerful than what we normally observe from the Sun. That makes the environments around them unpredictable and, at times, extremely harsh. In 2016, a new discovery turned this star into the center of attention for astronomers. Astronomers announced the discovery of a planet orbiting Proxima Centauri, a rocky planet with a mass similar to Earth's, located within the region where temperatures could allow liquid water to exist on its surface. That planet was named Proxima B. Almost immediately, Proxima B became one of the most important observational targets in exoplanet research. For the first time, the nearest potentially habitable world to us was no longer a hypothetical idea. It had a name, an orbit, and could be studied using real observational data. However, the data that emerged afterward led to another question. Does being located within the habitable zone truly mean that a planet can support life? From the moment it was announced in 2016, Proxima B quickly became one of the most extensively studied exoplanets. What attracted so much attention to Proxima B was its orbital position around its parent star. When evaluating a planet's habitability, the amount of energy it receives from its host star is always one of the first factors to be considered. If the energy is too high, water on the surface is unlikely to remain in a liquid state for long periods of time. If the energy is too low, water tends to freeze. Between those two limits lies an orbital region where liquid water can exist if other conditions are favorable. Initial measurements showed that Proxima B lies within this region. Among the thousands of exoplanets discovered so far, it is one of the few that both appears to be a rocky world and occupies a zone where liquid water could potentially be maintained. Current data indicate that the planet has a minimum mass of about 1.17 times that of Earth. Although its mass alone is not enough to determine its internal structure with certainty, current models generally favor the possibility that Proxima B is a rocky planet. Proxima B completes one orbit around its parent star in only about 11 days. However, because Proxima Centauri is a dim red dwarf star, that distance still allows the planet to receive an amount of energy considered compatible with the existence of liquid water under certain conditions. Soon afterward, researchers began asking a series of questions about the planet's actual environment. Does this planet have an atmosphere? Can water exist on its surface? And are the physical conditions stable enough to maintain a suitable environment over long periods of time? Other models examined the role that oceans might play in regulating the planet's global climate. Although no final conclusions have been reached, early models generally suggested that Proxima B may not be a completely hostile environment for liquid water. But it is here that another problem begins to emerge. The very distance that allows Proxima B to receive enough energy for liquid water may also create an entirely different consequence. If that is indeed the case, Proxima B would not experience day and night cycles in the way we usually imagine. And if that is true, then the entire way we think about a potentially habitable planet may have to change. From the very first studies of Proxima B, scientists realized that the planet's orbital position could produce a very important consequence. Proxima B takes only about 11 days to complete one orbit around Proxima Centauri. This distance is close enough for Proxima Centauri's gravity to strongly influence the planet's evolution. As a result, Proxima B has most likely entered a state known as tidal locking. In this state, the planet orbits its star in exactly the same amount of time that it takes to rotate once on its axis. The result is that one hemisphere always faces the star, while the other hemisphere never sees it. If this is indeed the case, Proxima B would not experience day and night in the familiar way we do on Earth. Lighting conditions across each region could remain nearly unchanged for extremely long periods of time. And it is here that climate-related challenges begin to emerge. Being located within a region where liquid water could potentially exist was one of the main reasons Proxima B attracted so much interest. But as more detailed climate models began to appear, attention shifted to a different question. What would happen if all of the energy from the star were continuously concentrated on the same side of the planet? Tidal locking does not simply alter illumination conditions. It can reshape an entire planetary climate system. Some of the earliest models proposed a rather extreme possibility. According to these models, the hemisphere facing the star could become significantly hotter because it receives a constant supply of energy, while the opposite hemisphere continuously loses heat to space. If heat transfer between the two regions is not efficient enough, environmental differences across the planet could become extremely large. But later results did not entirely support that picture. Tidal locking does not automatically divide a planet into two completely separate worlds. The final outcome depends on many other factors, particularly the atmosphere, surface pressure, the presence of water, and the planet's ability to transport heat on a global scale. At this stage, the focus of research was no longer Proxima B's position in space, but how its entire climate system responds to tidal locking. And the answer may lie on the very hemisphere that always faces Proxima Centauri, the side that receives all of the energy from its parent star. If Proxima B is indeed tidally locked, there would be a region that always faces Proxima Centauri. This is the region that receives most of the energy from the star. At first glance, it may seem like the most favorable place for liquid water to exist, but the problem lies with the star itself. Proxima Centauri is a dim red dwarf, which means Proxima B must orbit very close to it in order to receive enough energy. That very proximity places Proxima B under the direct influence of its parent star's activity. Observations show that Proxima Centauri is a highly active star that frequently produces energetic outbursts. During these periods, the environment around the planet can change significantly over short timescales. For a planet orbiting so close to its star, such outbursts may become a regular part of its environment. The challenge is that we still do not know exactly what exists on the surface of this planet. To date, no telescope has directly observed the terrain, oceans, or atmosphere of Proxima B. Because direct observations are not yet possible, most of our current understanding still comes from climate models. In most of these models, the atmosphere is the key factor controlling temperatures on the hemisphere that permanently faces the star. If the planet possesses a sufficiently dense atmosphere, some of the heat can be transported to other regions through large-scale atmospheric circulation. On the other hand, if the atmosphere is too thin or has been significantly depleted over time, its ability to redistribute heat would be greatly reduced. In that case, environmental differences across the planet could become much more pronounced. If water exists on Proxima B, it could directly influence the planet's global climate. Water is capable of absorbing, storing, and transporting heat, helping to reduce extreme environmental variations. As a result, the hemisphere that always faces Proxima Centauri has become the most important region in climate models of this planet. It is also where researchers search for the first clues about how Proxima B actually functions. However, every scenario leads to the same consequence. If one side continuously receives energy from the star, then the other side must exist under completely opposite conditions. And that leads to the next question. What is happening on the half of the planet that never sees light from Proxima Centauri? If one hemisphere of Proxima B always faces its star, the opposite hemisphere would exist under completely different conditions. This is the region that never receives direct light from Proxima Centauri. There is no sunrise, no sunset, no moment when the star appears above the horizon. And it is also the region that has produced some of the most varied results in climate models. Heat continues to escape into space, but the supply of energy from the star is virtually non-existent. As a result, this region tends to become colder over time. Exactly how cold it becomes depends on the planet's ability to transport heat from the illuminated hemisphere. If the atmosphere is sufficiently dense and efficient, heat from the day side can be carried to the night side through global-scale atmospheric circulation. If oceans exist, they may also contribute to the redistribution of heat. As a result, current models still produce very different scenarios for the dark hemisphere. In some models, the atmosphere is capable of maintaining relatively stable temperatures. In others, less efficient heat transfer allows the region to become significantly colder. Water is the factor that receives the most attention in this region. If temperatures remain too low for long periods of time, water could freeze and accumulate on the surface. This process could affect the planet's entire climate system, The more water that becomes trapped as ice, the less water remains available to participate in atmospheric processes. Another possibility is that part of the atmosphere could condense in the coldest regions. However, that depends on atmospheric pressure, chemical composition, and the planet's evolutionary history, factors that we have not yet been able to determine. Even so, the dark hemisphere may not be as quiet as we imagine. If Proxima B possesses an atmosphere, air currents could continuously move between the two hemispheres, transporting energy from the illuminated side to the side immersed in darkness. In that case, the boundary between the two hemispheres would simply be one part of a single climate system. But neither the illuminated side nor the dark side has become the primary focus of attention. Instead, attention has gradually shifted to the region between the two halves of the planet. A transitional zone where heat, atmospheric circulation, and environmental conditions may reach a more stable balance than anywhere else on Proxima B. And it is this region that has begun to appear in an increasing number of climate models of Proxima B. But the results from many climate models point to the same region. That region lies between the two halves of the planet. Astronomers call it the terminator zone, the transition region between light and darkness. If viewed from space, it would appear as the boundary encircling the planet, where the light from the star gradually gives way to darkness. On Proxima B, this may be the most important region on the entire planet. The transition zone may receive just enough heat to avoid the extreme conditions found on either side. In many climate scenarios, global atmospheric circulation could transport heat from the illuminated hemisphere to the dark hemisphere. This process could create more temperate regions along the transition zone. In many scenarios, the most favorable location for liquid water is not at the center of the illuminated hemisphere, but near the boundary between light and darkness. If water exists on Proxima B, it may be concentrated in regions that are neither too hot nor too cold. However, this entire scenario only makes sense if Proxima B actually possesses an atmosphere. Without an atmosphere, heat redistribution would become far less efficient. The temperature difference between the two hemispheres could increase dramatically and completely alter current predictions. On the other hand, if the atmosphere is sufficiently dense and remains stable over long periods of time, it could become the factor that helps maintain more favorable conditions within the transition zone. If oceans exist, they could participate in transporting heat alongside the atmosphere. That is why the transition zone appears more and more frequently in studies of Proxima B. Not because it has been proven to contain water or life, but because, based on the data currently available, it is the region where the greatest number of favorable conditions for both possibilities converge. If life ever emerged on this planet, it may not exist on a global scale. Instead, the entire habitable environment could be confined to a narrow band stretching around the planet. A region that belongs neither entirely to the light nor entirely to the darkness. But even if the transition zone exists, the story does not end there. Conditions suitable for liquid water do not automatically mean conditions suitable for life. The environment around Proxima Centauri is influenced by another factor, one that may determine the fate of the entire planet over billions of years. That factor is the violent activity of the star itself. But even if the transition zone truly exists, the challenges do not end there. Nearly every model encounters the same question. That question is the very star this planet orbits. Proxima Centauri is one of the most extensively studied active red dwarf stars known today. During periods of stellar activity, the environment around the planet can change dramatically over short periods of time. What makes Proxima Centauri particularly important is that a potentially habitable planet orbits extremely close to it. That same proximity also exposes Proxima B to a far harsher space environment. the greatest threat does not come from visible light. The physical processes taking place on the star also generate high-energy radiation and streams of charged particles that travel into the surrounding space. If a planet lacks effective protective mechanisms, its atmosphere can be affected over time. For this reason, a magnetic field has become one of the biggest unanswered questions surrounding Proxima B. On planets with strong magnetic fields, some of the charged particles emitted by the star can be deflected before they reach the atmosphere. This helps reduce the direct impact of the space environment. But at present, we do not know whether Proxima B possesses a magnetic field strong enough to provide such protection. Scientists have also not yet confirmed whether the planet has an atmosphere at all. Some models suggest that an atmosphere could survive for long periods of time. Other models indicate that the star's activity could significantly erode that atmosphere over billions of years. So far, no direct observations have been capable of definitively resolving this question. As a result, Proxima B remains one of the most debated exoplanets currently known. On one side are models suggesting that the planet could retain an atmosphere, efficiently redistribute heat, and create regions with relatively stable conditions. On the other side is the possibility that the environment around the star has stripped away many of the ingredients necessary to support liquid water over long periods of time. Both possibilities are supported by legitimate scientific arguments. What is still missing is data detailed enough to determine which scenario truly applies to Proxima B. After nearly a decade of research, we now know the planet's location, mass, orbit, and the basic characteristics of the star system it inhabits. But the factors that ultimately determine its habitability have still not been observed directly. Proxima B remains suspended between two very different possibilities. A planet capable of maintaining favorable conditions for an extremely long time, or a world that lost most of those conditions billions of years ago. When Proxima B was announced in 2016, many viewed it as the most promising candidate in the search for life beyond the solar system. It was a rocky planet, located within a region where liquid water could potentially be maintained and belonged to the closest star system to us. But nearly a decade of research has raised more questions than answers. Today, Proxima B is no longer simply a planet located within the habitable zone. It has forced scientists to reconsider how we evaluate the habitability of a planet. For many years, the presence of a region capable of supporting liquid water was considered the most important criterion. But Proxima B has shown that this is only the beginning. Beyond the question of distance from the star comes a long list of other questions involving the atmosphere, magnetic field, stellar activity, heat circulation, and the planet's evolutionary history. A world may occupy exactly the right position and still face environmental conditions completely different from those predicted by simple models. The questions surrounding Proxima B also reflect a major shift in exoplanet research. Rather than focusing solely on orbital position, scientists are becoming increasingly interested in the entire system in which a planet exists. How does the host star behave? How does the planet respond to its surrounding environment? And can stable conditions be maintained for a sufficiently long period of time? That is also why future observations are expected to provide data that we currently lack. The focus is increasingly shifting toward understanding the actual environments of already discovered planets. The goal is to determine the composition of their atmospheres and search for signs of water, oxygen, methane, and many other compounds that could help us better understand conditions on these distant worlds. For Proxima B, many important questions remain unanswered. We do not know whether this planet has an atmosphere. We do not know whether water exists on its surface. We do not know how strongly the eruptions from Proxima Centauri have affected the planet throughout its history, and it is precisely these gaps in the data that keep the debate surrounding Proxima B alive. So far, Proxima B has not provided evidence that life exists there. Instead, it has become a focal point for some of the biggest questions about climate, atmospheres, and the habitability of rocky planets. Future observations may reveal that Proxima B is far more hostile than current predictions suggest. They may also show that the planet has managed to maintain stable conditions for a very long time. At present, there is not enough evidence to support either conclusion. For now, the most important factors that determine the habitability of Proxima B remain beyond the reach of direct observation. And until we can observe that world in greater detail, the question that has existed since Proxima B was first discovered remains unchanged. Is this truly a habitable planet, or simply a world that appears promising from a distance of more than 4 light-years? For many years, Proxima B has been regarded as one of the most promising places to search for life beyond the solar system, but the data that emerged afterward raised more questions than answers. This planet lies within a region where liquid water could potentially be maintained. Its mass is consistent with that of a rocky world. It orbits the closest star to us. At the same time, it must exist in an environment strongly influenced by tidal locking and the activity of its host star. To this day, we still do not know whether Proxima B has an atmosphere. We do not know whether water truly exists on its surface. We also do not know whether those conditions can remain stable for a sufficiently long period of time. These unanswered questions have become the primary focus of current research. So far, Proxima B continues to raise more questions than it answers about the habitability of a planet. Each new study and each new generation of telescopes adds another piece to the puzzle surrounding this world. More than 4 light-years from Earth, Proxima B still appears only as a faint signal within astronomical data. Yet from that small signal, one of the greatest scientific searches of the modern era continues. And until the first direct observations become possible, the biggest question surrounding Proxima B will remain. Could the closest known planet beyond the solar system truly be a habitable world? If you enjoyed this journey into the exploration of worlds beyond the solar system, don't forget to like the video, share it, and subscribe to the channel so you won't miss future stories about the universe. Thank you for joining us all the way to the end of this journey, and I'll see you in the next video.